Get that going. So we may have to adjust the quality, especially if I kick it. There's a seat here, a couple of seats over here. I know a couple of stories about seats. Older professor I know from Georgia State, he said when he was an undergraduate at Harvard back in the 70s, they had seats in there you couldn't even see the board. About 500 students in that room. I've heard other such stories. All right, don't blame me for whatever. We opened up 15 additional seats because a number of you were on the wait list. If there's any issues, we can take care of it, but hopefully we'll be all right. It's packed. I'm not elbow room. Let's see. Handout. How are we doing on the handouts? Everybody got 3 handouts? Okay, well, I'm Chad Stevens, your instructor, doing something a little bit new this semester. It's everybody combined in one lecture. You have 6 different labs. I teach the Monday lab. There's other instructors for the other 5 labs. Okay. We can start with the syllabus, one of the white packets. Y'all here? Okay. Well, I'll say this right now. I think it's going to be fun. All right. Hope you're looking forward to it. Organic chemistry. The chemistry of cool stuff. Yeah, it is cool. Cool stuff is it's like Dutch for what? Carbon. Chemistry of carbon. There's your syllabus. Here. Okay. Let me point out the textbook. Textbook of record is by Klein. This is the hardback version. The version we have in the bookstore here is a paperback version. Save you a little bit of money, but you can probably still get this hardback on Amazon cheaper than that. Basically, I don't have you in the textbook. I don't require much, okay? I don't require homework. Because of that, you can use any book you'd like. All organic textbooks have the same material, okay? Recovering hybridization. Okay, any textbook is going to have that material. That's why I say you can really use any textbook you like. If you want to check with me to make sure, that's fine. I do recommend you have a solutions manual with it. This is the textbook of record. Go to the bookstore, solutions manual. You know, I'm a little old school, I like hard copy, so I have that here. You guys might like a PDF or something, but whatever book you have, I recommend solutions manual. Because importantly, you got to be doing problems. You got to be checking your answers, learning from what you're doing. Okay. Klein book has got a good bit of medicinal chemistry stuff in there, which is my background. I know a number of you are interested in medical field. I will use drug molecules to illustrate a lot of organic principles. Okay, there's also a laboratory techniques book that's on the syllabus. This is Morrig, 4th edition. One in the bookstore. I saw like 1st or 2nd edition on Amazon for a penny, $3.99 shipping. Okay. Most of all your techniques, they're all the same. Okay. These are just the books of record. If you want to spend a lot of money, get these books. All right. Let's see. I also have, particular for me, is I have a workbook and lab manual. I used to give out even more handouts with like my own homework problems. So you'll see types of questions you'll have on the test. Eventually I just sort of put these all together and made a workbook out of it. Answer keys included. There is a table of contents. Also in this now is the lab manual. In the back there's a table of contents for the lab manual. It contains all the labs we'll be doing. It also has information like guidelines to notebooks, guidelines to lab reports, Checking in the lab, some of you already checked in the lab yesterday. Stuff like that. Instructions for using the IRs, washing glassware, etc. On the back of the second page of the syllabus is a daily outline. Back to the second page. Tuesday, Thursday, those are our topics. It's not all of them. It's mainly, just what I can fit into the little grid there and sort of the main ones. But on the far right is your lab for the week. Okay? So next week, everybody will be doing solubility of organic solids and various solvents. Okay? That's the lab you're doing. Please don't think you're doing first lab in here or whatnot. Okay? These may not be in order. We may not be doing some of these in here. Okay? I've had students show up before prepared to do the wrong lab because you did not look right here what we were doing this week. That's what you're doing. Okay. I'm not going to go over the first couple of pages. Everything's there for you to read. That's basically assignment number 1. And on Thursday, at the beginning, I'll see if you have any questions about the syllabus. Okay. I will say one thing. The lab manual portion was written, or it'll refer to a book called Zubrick. Zubrick was the alternative to this. I thought we were going to switch to Zubrick. We ended up sticking with Morig. So anytime it says Zubrick, it means Morig, this book. Okay. Okay, I'm not going to say much of what's here. I'm going to tell you something different. Basically, organic chemistry is a class that builds upon itself much more than Gen Chem. The things we do week 1, we will then go on week 2 and use that stuff, and then week 3 we'll go on and use the stuff we use in week 1 and 2. Builds very much. If you get behind, come week 3, 4, you're going to already be lost, and certainly by the time we get around midterm, you pass because you didn't keep up. You got to keep up. Same thing going into organic 2. You get into organic 2, you're going to be expected to know what was taught in organic 1. That's your foundation. Okay? So it builds. Same thing goes for the lab. You do a lab early on, okay? Maybe a month down the road, you're going to use that same technique. You need to be ready to go, okay? You can't just do something and forget about it. We do things, we teach you stuff for a reason. So we think we build upon that and go on and use it a couple of weeks later. Okay? You get to organic 2 lab, you're going to be expected to know all the techniques for organic 1. Don't have time for you to be in lab and not know what you're doing. Okay? Just keep that in mind, guys. Everything is done for a reason. We're building. Okay? Got to stay on top of it. The main reason students don't do well sometimes in organic chemistry is because it just becomes overload because you kind of slacked off a little bit and it got too much. If you don't slack off and you stay engaged, a couple of other important things is you got to ask questions. If you read the syllabus, I talk about jotting down your questions in a composition notebook or whatever device you want to use. Okay? And then getting your questions answered. A lot of times I'll say questions. Okay? My dream is to say questions and you all go, I got a question. My nightmare is when I say questions and everybody just kind of sits there. I don't see how you can study organic chemistry and not come up with questions. Write them down. Why write them down? Maybe you're studying, you come up with 10 questions. And you come see me or something and you only remember one of them. Well, what happened to the other 9? Write them down, get them answered. I also talk about when you come to office hours, bring this type of thing. Also bring your textbook. I want to look at what you're reading in the textbook and what type of homework problems you're doing. Other big thing is following directions. Okay? I'm big on, there's directions written in the lab manual. That means you're expected to read, follow. If there's something you don't understand about directions, then please ask and I'll clarify. All right? I'm not going to take time to read you the directions or rehash them. That's a waste of our time. Time is very precious. You want me to go into details, questions, which you have, not written stuff. Okay. Let's see. Here is a common list of or a list of common drugs. A number of you know these. Tylenol, Aleve. There'll be a lab experiment where we use Aleve, do photogrammetry on Aleve. And so basically, 90% of your drugs, 95% are small organic molecules. These are the types of molecules we're going to be studying. Physical properties, reactivity, structure, bonding, spectroscopy, synthesis. Just look at prilosec. We also quickly need to become how to interpret or use these line bond structures, where each point is a carbon. Heteroatoms such as nitrogen, oxygen, sulfur shown, whatnot. Coming up with formula, we got to know where hydrogens are. Hydrogens aren't shown on carbons, etc., etc. But it's just amazing that this small collection of atoms put together in this way can be used to treat a lot of bacterial infections, right? And a lot of people making a lot of money on these drugs, small compounds, because they know how to make them, and they know how to investigate their activity in the body because they're familiar with molecular biology and organic chemistry. So there's lots there. You'll see lots of drugs in the homework problems in the workbook. Types of questions. You see ibuprofen over here, shown at the top in a generic, but we also can be shown in stereochemistry with a dashed and bold bond. Okay, stereochemistry will be big in test 2 of the 3 tests that we'll have here. Questions. What's the chemical formula? What do the dashed and wedges mean? What type of bonds make up the structure? Hybridization, functional groups. Is ibuprofen acidic or basic? How would you prepare a salt of ibuprofen? What does racemic mean? What's an enantiomer? S and R, plus or minus. This is all the language and general topics of organic chemistry that we'll be covering first and second test. As we move on, we'll do more and more synthesis, functional group transformation. How do you make ibuprofen starting from, say, benzene? Well, somebody out there doing it and selling it to you and making lots of money. There's some more advanced questions. You go into courses like biochemistry, or you go to medical school or dental school and take pharmacology. You could see questions like this. As I said, that information you need to know to answer more advanced questions. Anybody want to get a job one day? Here's a job ad. It's probably 10 years old, but there's plenty out there, every month, like CNN News. If you look at what they want, it basically reads like a syllabus for this course. They want people who know structure and reactivity of organic molecules. They want you to be able to understand spectroscopy, functional group reactivity, how to purify compounds. Basically, the stuff hopefully is going to be very practical. I don't particularly like to teach stuff just for fun of it. I like to teach you stuff that's going to be useful, that you can go on and excel in your future classes, or you can go get a job, or you go to the research lab and do something. Okay? If I don't see much use in it, I'm probably not going to be talking about it. On the back, there you go. How to fail organic chemistry. Anybody interested in failing? If you're interested in failing, there you go. My little sarcastic page there. Do all these things, and you're probably not going to do well in class. Okay, a lot of this is sort of stuff we need to get out of the way here. As I said, my background's in drug development, medicinal chemistry. I actually graduated from this university. I was called Augusta College. Went to the University of South Carolina. College of Pharmacy, I got my degree in medicinal chemistry, which is the organic chemistry of drug design. Then I went on to Georgia State. I was there for about 7 years doing postdoctoral research, working on compounds for protozoal diseases like malaria, leishmaniasis, drugs for that. I also have research projects, drugs for antivirals. We send compounds over to Belgium. We have a collaborator over there to test our compounds. Getting a little bit more into cancer, just a wee bit, trying to explore that. Let's see. The green sheet is our outline. I'll typically put like outlines on colored sheets. First thing we'll do is review of atomic structure. The other handout is the one I sent you by email today. I wanted you to print it, but I decided to hand it out instead because we might get there today. All right. Oh, a couple other things. Forever I've always taught IR after we check in. Check in the lab, 45 minutes, and then we'd come downstairs for the remainder of the first week lab, and I would give IR lecture. Okay? About 2 hours of lecture there, with a break in between. Because there's 6 lab sections, I'm not doing it this time. Okay? Instead, I put those lectures on YouTube. They're not old. They were done about a week or 2 ago, just me to the camera. Okay? Hopefully there's a little bit of excitement to them. Just in an empty room. But they seem reasonable. But your assignment is to watch the 2 videos. You do need the handout that goes along with the lecture. I sent that by email, and I expect you to print that one. I'm not going to pass that one out in class. Okay? IR will be on test 1. There are IR questions in the workbook. Okay? At some point in a couple of days, I will say, is there any questions about IR? We'll see how that's going. Okay. If you go to my YouTube page, it's in the syllabus. I think you just search my name now. And if you go to playlist, you'll see like IR lectures. You'll also see lab demos. I'll be doing a little bit more of that. Historically, I just kind of stood up front for the first 15 minutes of lab. But again, that's valuable time. Instead, I'm going to ask you to watch a short video before you come to lab. Okay. We'll do at least one of those, perhaps more. Questions while I'm thinking here. Techniques. Composition notebook. Write down your questions. Anybody need one? I mentioned note cards. Good way to write information on one side. And then on the back side, you sort of have answers. Okay. There's different ways to do this, but it can be useful. Probably more as we go into the later part of this and into organic too. Anybody need some note cards? So I'll hand them up here first. Can you catch?
I don't want to hit anybody. Heads up.
Other handouts? What are you missing? Other handouts? Where are the handouts at? If you have to pass all the handouts, just forward. Question?
Yeah, I know that with the textbook there's an access book for the online stuff. Can you do that? I know that's
It's discussed in the syllabus. Not required. Okay. What do I require? I require you to make the grade of 70 average for the course to pass. That's what I require. Okay. No, I don't like to require a lot of things. I don't require you to come to class. I don't require you to get out of bed in the morning. Questions? Green sheet? Green sheet? Pass the green sheet back, please. Other green sheets? Okay. Probably need to make more copies so they... But we're going to figure out how to do the passing out of the handouts. Okay, there's probably a number of things I've not talked about. Please read the syllabus. We'll see what we need to talk about on Thursday. Others are checking into lab this week. You got your lab date and you signed up for the course. Question?
Can we have a PDF
Of the what?
The lab techniques manual.
I don't know if I can do that. It's sort of like mine.
No, I mean like the blue book. Like, so you have a PDF of that.
Oh, you mean the techniques book?
Yeah.
Oh, yeah. You can have PDF of anything.
Yeah.
Whatever you want. From me?
Yeah.
I don't have it.
Oh no. Did you think that I was asking you for that book?
No, I thought you were asking me for this.
Yeah, I wasn't.
No, you can have whatever works for you. Okay? You need to be doing problems. All right? As we get going, you'll see. Hopefully. If you don't see, then ask. But again, the main thing, you need to work problems. I'll say more on Thursday. I want to get us going, okay? Any other questions? We'll get going. The other handout is functional groups. We may or may not get to that. I thought we might. That's why I went ahead and gave it to you today. Okay, green sheet. Structure and atomic structure. All right. It's always a little bit tedious to get us going here. All right. So I could talk probably an hour and keep talking, but you just need to get going. I need you to ask questions. Perhaps. Structure and bonding. Okay. Well, chemistry of carbon. Periodic table right here.
Where's the dextrose?
There's a periodic table in the back of the Workbook Lab Manual. Okay. So, carbon. What's the atomic number of carbon?
12.
Atomic number?
12.
6, isn't it? Then we got, what, mass number?
12.
Right, something like that. Everybody said 12. Why not something else? Well, protons, neutrons. How many protons?
6.
6. How many neutrons?
6.
6. How many electrons?
6.
6. 6, 6, 6. There you go. Perfect depth. This is in the neutral, right? It can have more or less, and it will be charged. All right. We can come over here. 13. Do we need to really put a 6 there?
Yep.
No. Every carbon is 6, so that's usually not written. C13 would have how many protons? 6. Every carbon has 6. If you don't have 6, it ain't carbon. How many neutrons?
7.
7. How many electrons, assuming it's neutral?
6.
All right, so the difference is we got an extra neutron. What's the relation between these two?
Isotopes.
Okay, if you can't see or something, say, hey, I can't see. So C13 is an isotope. What else do we have? C14. Okay, that's just, what's the difference?
1 more neutron.
What's that, 8?
Yes.
8 neutrons, 1 more neutron. Isotopes vary by number of neutrons. What's the natural abundance? Carbon 12. Natural abundance of carbon 12. The carbons in your body, what percent are carbon 12?
Like 99.
About 99%? How about carbon 13?
0.
About 1%? How about carbon 14? Well, it's in the noise. I mean, it's very minor. Okay, this was rounded off. Okay, very minor, negligible, but it is significant because what do we use carbon 14 for?
Dating.
Carbon dating. Okay, because it's radioactive. C13 is important for NMR. NMR is probably the most important spectroscopy in organic chemistry. We'll see NMR in organic too. That uses carbon 13. Only 1% of the carbons are NMR active, though. Carbon-12 is actually not NMR active. That's one of the limitations of carbon NMR, although it's not that bad. So natural abundance here. So that's important. Basically, you need to know stuff under 1. Protons, neutrons, where are they? Where are the protons and neutrons at? And where are the electrons?
Cloud.
Not the nucleus. They're in the around the nucleus, right? Somewhere out there. All right. Electron configuration of carbon. Let's see. How many valence electrons does carbon have?
2.
4. Let's see. I haven't had chem in a long time. I think it's 1s. What's next? 2s? And then 2p? And carbon has how many electrons?
6.
1, 2. What are we using? Aufbau principle, Hund's rule, Pauling exclusion principle. 3, 4, 5, 6. Yeah. What do we call these electrons?
Valence.
Valence electrons. These are kind of the core or subshell electrons. Valence electrons are important. Those are the ones that govern all the bonding. And so typically, eventually, maybe in like a minute, we'll talk about why carbon makes how many bonds?
4.
4. Basically, each bond gets an extra electron. It needs 4 more electrons to get a full octet. Okay. So then all the valence orbitals will be full. 2, 4, 6, 8. Needs 4 more to get 8. But very importantly, that's ground state configuration. About all the time in organic chemistry, the atom will undergo hybridization or exist in a hybridized state. We will mix these orbitals. I'm not sure I can tell you what the purpose of ground state really is. Types of orbitals. What does an S look like?
Circle.
Spherical, like a volleyball, with electron density approaching the nucleus. What's a p orbital look like? Now we have this dumbbell shape with actually no electron density at the nucleus. Most of this should be reviewed. But also importantly, when we start hybridizing, we're going to mix these orbitals together. Okay, and they'll have different shapes. It's actually on the back of the one handout packet. Some crude drawings of the shapes. And those shapes will affect things like bond strengths and bond lengths, etc. So we'll move away from the ground state and the simple orbitals to hybridized configurations of orbitals. Need to do some reading on that, be prepared for all that. Anything else on number 1? Did we hit everything? Roman numeral 2, bonding. Good time to ask questions when I'm erasing. By the way, what about carbon 11?
It's not a
What?
It's not stable. It's only one valence. Or I'll only have one in the
I'd have to think about that more, but carbon 11 is man-made. It's radioactive. It's not natural, but it can be man-made. Carbon 11 is used for some of the like PET imaging in the medical field. Okay, so carbon 11 is becoming a little bit more important, but it's man-made. Bonding. All right, let's see if we can ease into bonding here. Let's see. Well, you got an H atom, okay, 1 electron, right? Need a periodic table. What does H want to be like? It want to be like helium. That's all you got on the first row. It wants 2 electrons, not an octet, but a duet. How do we get another electron? One way to do it is to say, hey, these 2 H atoms could pair up we can get sort of something like this, and this becomes a bond, and this becomes sort of orbital overlap between the two hydrogens. And then ultimately we can draw this like this, and that's a 2-electron covalent bond, which means that. Now that thing right there, that could be the topic of an entire course, okay? There's books written about that. We're not going to go too much into that, okay? P-Chem, a lot of math, huge amount of stuff you could talk about there. I'm basically saying overlap of interaction of 2 electrons in an orbital. You can even get into molecular orbitals, 2-electron covalent bond, sharing of electrons, as opposed to this one stealing that one and making ions. And then we call this what? H2. And we know H2 is hydrogen gas. But the other important thing here is whenever you start making covalent bonds, you can satisfy both atoms at the same time, because you can say, hey, that H gets to count those 2 electrons, and it now has 2 electrons around it, and it's now completed its valence orbital. And then you can say, well, that H has also completed its valence orbital. If they're sharing, they both become happy. Now carbon, I'm going to come back over here. So H started with 1 electron. That's all it has. Put up a carbon, how many electrons are we starting with?
4.
Started with 4 electrons. Now I'm going to put these 4 electrons around it as 4 different, dots. Carbon wants to achieve an octet. It wants 8 to fill its valence orbitals. We can get it 8 by bonding to something else. Well, what about hydrogen? Hydrogen has 1 electron. We can bond this to an H, and I'll draw this as an X. Okay, the 1 electron. So 1 electron can come from H, 1 electron can come from carbon, and now we have a 2-electron covalent bond. But we can do that 3 more times. X from H, X from H, X from H. Now we can look at this and say, well, we can turn this into just a line bond, where that's bond to H, bond to H, bond to H, bond to H. But this carbon now, because we can count all these electrons as sort of for the carbon, how many are around the carbon? 2, 4, 6, 8. So the carbon has an octet. But then look at the H. How many electrons around the H?
2.
These 2 get to count from each H, so the H has a duet. So the H electrons, valence shells are filled, carbon shells, valence orbitals are filled. And so ultimately, carbon starts with 4 electrons. It needs 4 more. Each bond gets you an electron, essentially. That's why carbon makes 4 bonds. So we can kind of catalog this. Carbon is what? 4 bonds and no lone pairs. You'll see this change. If we go to nitrogen, which is next on the periodic table, not up there. How many valence electrons?
5.
5. Okay, we move to the right 5. I'm going to go 1, 2, 3, 4. Now I'm going to pair up. 5th one paired up. How many bonds does this nitrogen need to make to become happy? 3. If I'm using H, I can bring in an H with that single electron, bring in H with that single electron, bring in H with that single electron, and we can have a happy molecule like this. And so this would be nitrogen with 3 bonds to H, and then what else is there?
A lone pair.
A lone pair. Lone pair, non-bonding pair. So this is typical bonding for nitrogen. H, 2 electrons around it. H, by the way, is always on the periphery. H only makes 1 bond. Nitrogen has how many around it? 2, 4, 6, 8. Lone pair counts as 6, 7, and 8. So now the nitrogen has an octet. 8 electrons around it, right? How many valence orbitals does it have? 4. 2 electrons each for a total of, they're all filled. Okay? Now we're not talking about hybridization yet, but these are your valence electrons. To fill them all up, how many do you need? 2, 4, 6, 8. That's what we got here with the sharing thing. Okay? This is standard bonding I'm putting up here. Standard bonding for nitrogen is 3 bonds, 1 lone pair. Standard bonding meaning no charge, standard bonding. Now, if you see a nitrogen without 3 bonds and 1 lone pair, it's probably going to have a charge. Okay? It's going to be non-charged, kind of standard. What's after nitrogen? Oxygen. How many valence electrons? 6. 1, 2, 3, 4, 5, 6. How many bonds do we need to make?
2.
1 to H. Another 1 to H. What do we got?
Water.
2 bonds to H and 2 lone pairs, right? That's what that indicates. Oxygen has an octet. 2, 4, 6, 8. 8 electrons around it. 2 of them had to come from the things that bonded to, because it only came to the dance with 6. Through covalent bonding, we can now count it as 8. Hydrogen, 2. Every hydrogen has 2. Right? We're just doing simplistic looking at bonding and why things have a certain number of bonds. This is standard for oxygen. By the way, it's also standard for what's under oxygen. What is under oxygen? Sulfur. Selenium. What's next? Tellurium. Is that right? They all have the same bonding. So what do we got here? 2 bonds and 2 lone pairs. Standard bonding for oxygen. What's after oxygen?
Fluorine.
Fluorine. One of the best elements on the periodic table. If you look on my door, it talks about when fluorine was first discovered, and they got some back in 1890, and some of it fell on the floor, and it says the floor instantly took fire. The floor was wooden. As soon as the fluorine hit it, it turned into fire. Fluorine, very reactive. Reacts with any organic stuff. Lots of people have lost fingers and arms working with fluorine chemistry. Look up HF. Some nasty stuff there. Fluorine. Okay, how many valence electrons?
7.
7.
1, 2, 3, 4, 5, 6, 7. Why do I only go around 4 times and then start pairing up?
Because you have to fill, it's the exclusion principle, you have to fill all the spots before you can double up.
Yeah, you sound like you know what you're talking about. I was looking for more simpler. Simpler is how many advanced orbitals are we dealing with?
4.
Yeah, I'm really putting electrons in 4 orbitals. I don't have 5 orbitals, I only have 4. So I did 4, and then I started putting more into one of the orbitals. Really, the 4 orbitals. Very simplistic, though. I just need 1 bond. And then I can bring in that H, and then I can make that, and we get, what, HF? That's that nasty stuff. Whew. couple of drops of that on your skin, and you're not going to make it. So what do we got? Very often lone pairs will be omitted, okay? You got to know they're there. So what's standard bonding for your, what do we call the fluorine, chlorine, bromine, iodine? Halogens. Halides when they're minus. What's standard bonding for halogens?
One bond,
One bond.
3 lone pairs.
One bond, 3 lone pairs. Okay? It's just standard bonding because fluorine just needs 1 electron to get 8. It can bond to H, or it can maybe bond to carbon. It can bond to anything. I just did H's here. I mean, this could be a bond to fluorine. You know, I don't write this down, but this could be a bond to fluorine, and the remainder would be fluorine lone pairs. Fluorine 19 is also used heavily in PET imaging. I'm sorry, not 19, fluorine 18. Fluorine 18 is radioactive. Okay, now when we draw the 2 electron dash covalent bond, the lone pairs, this is called the Lewis structure. Okay, we're showing all valence electrons either as bonds or lone pairs. Gilbert Lewis, who by the way wrote that big book on the nature of the chemical bond, not that thick, classic book, probably written back in the 30s or so. Let's see, what have we done here? Definition, typical, noble gas, octet rule. Basically, you know, most these atoms are obeying the octet rule. They want an octet around them. H only wants 2 around it. You can expand the octet rule, but you can only do that when you have d orbitals. You only have d orbitals when you go down another row, like sulfur below oxygen. So using the d orbitals, you can see maybe 10, 12 electrons around the sulfur. You're never going to have 10 electrons around one of these second row atoms. Because if you only got 4 orbitals, the maximum is 8 electrons. If you start showing 10, I'm not sure where you think those electrons are going to be. The other handout has a miscellaneous page about atoms that have expanded octet. Take a look at that. Sulfur, phosphorus. Okay. We'll sort of go in stages. Simplistic. Let's move it up a notch. Get a little bit more detailed about bonding. Let's do this by trying to put together some structures. Some more atoms. Structures with single bonds. CH4O. Most of this review. All right, most of this seem like review? Anything new here? Any questions? Now, so typical bonding. We will see carbons with only 3 bonds. It'll have a charge. There is an exception. You can draw a carbon with only 2 bonds and no charge. So that's an exception. This is kind of a starting point. 95%, that's typical bonding. What we got here? CH4O. Okay, that's just formula. Formulas are listed C, H, and then alphabetical. Now you can also list formulas a little bit differently where they're sort of give some structural information. But a pure formula is written CH alphabetical. Okay, let's put together a structure. In some cases we can only do one. In some cases we may be able to put together 2 or 3 different structures. Let's see what we can come up with. I would recommend doing this first. How many valence electrons are we dealing with? Because remember, a Lewis structure, you show all valence electrons. Wouldn't it be good to know how many you're dealing with? How many we got here? How many for carbon? 4. How many for H? 1 times 4 equals 4. How many for O? 6. What do we got? Not 14? 14 valence electrons. Whatever we show should have 14 valence electrons. If your structure only shows 12, then you're not going to be right. Okay? Well, you think H is going to be in the middle? No. It only makes one bond. H is going to be on the periphery. Your halogens, because they only make one bond, those are going to be on the periphery. Here's what I would do. Okay. We got carbon. We could put H's around it, 4 H's, but then where would you put the oxygen? You wouldn't have any place to do it. Let's bond the oxygen to that carbon. We have 2 electrons on the board. I would recommend you put your hydrogens now on carbon. Fill the valence of carbon with hydrogens. We can put how many bonds to H?
1.
3. So now that carbon has 4 bonds and no lone pairs, standard bonding. All the H's are happy, the carbon's happy. How many we got on the board? That's 2, 4, 6, 8. We need to put 6 more. At this point, we have no more atoms. At this point, I would put your remaining electrons on your oxygen as lone pairs.
We have one more H.
Yeah, we have one more H.
Only 3.
Thank you. We do have another atom. Where do you want to put the H in?
On the
On the oxygen.
You can't go on carbon because carbon already has 4 bonds. All right? Got to go over here. 4. How many we got on the board? 2, 4, 6, 8, 10. We got to put 4 more up there. At this point, put them up here as lone pairs on your oxygen. The more electronegative atom likes electrons more. We're going to give it lone pairs. The more electronegative atom. How many lone pairs can we put here?
2 pairs.
2. And lo and behold, now everybody's happy. Carbon, 4 bonds, no lone pairs. Oxygen, 2 bonds, 2 lone pairs. That's standard bonding, right? I mean, there's the structure.
Professor, the name of this, is it methanol?
That's methanol.
Okay.
Yeah, 1 carbon alcohol. All right. Could you put these together another way? Could you put these atoms together another way? I don't think you can. All right. Let's repeat the process using C2H6O. Eventually we'll get into like C20 and whatnot. Question?
On the previous example with the, why can't you switch the lone pairs to the carbon and then replace the lone pairs?
Uh, 2, 4, 6, 8, 10, 12, 14. Okay, like that. Well, that's not typical bonding. You're going to have a charge. 2, 4, 6, 8. That is an octet. 2, 4, 6, 8. Everything does have octets. Problem is, while that may be a structure, I would strive for common bonding like we showed earlier. This is going to be, let's go ahead and do charge. Okay, what's the charge of this carbon if we show it like this? How do you do charge? Okay, this is how you do charge. First of all, I'm not going to give you a formula to do it. If you want a formula, look in your textbook. Here's how I do it. How many does carbon own here as we drew? Carbon owns 1 electron from each bond. Okay? It's like carbon had an electron, H had an electron, they paired up and made a bond. It owns 1 of each bond, and then it owns the lone pairs. So it owns 1 from that bond, 1 from there, 1 from that's 3, 4, 5. Carbon's owning 5 there. How many is it supposed to own? 4. It has an extra electron. If you have an extra electron, what's your charge? Negative. How many is the oxygen owning there?
5.
It's owning 5. How many is it supposed to own?
6.
So it's missing an electron. When you're missing an electron, what's your charge going to be?
Positive.
Positive. Okay? So there's charges. You got to know how to do charges. Remember, if it's not standard bonding, it's probably going to be charged. See, that's not standard bonding. It needs charge. Probably this right. This is a valid structure based on octets. This is not going to exist. I mean, this is the base. That proton is essentially going to quickly transfer to an acid-base reaction. It's just not a good structure. You like it for some other reason? Yeah. Yeah, we do need to get a sense for what are good structures. Okay, that can be a little bit difficult at the beginning. You say, hey, it's got an octet, which is a very important thing. At least you didn't put 10 electrons around the carbon, etc. It's not that good. Let's try over here. How many valence electrons are we dealing with?
20.
4, 8, 14, 20? Yeah. So we've got 20 valence electrons. Let's see. How about carbon, carbon, O? I'm going to put my H's on carbon. I got 6. We'll fill the valences of that carbon. Now happy carbon. Now that carbon's happy. 4 bonds, no lone pairs. I got what? 1 left? Here. How many electrons I got? 2, 4, 6, 8, 10, 12, 14, 16. And you can put 4 more. That's 2 lone pairs. Lo and behold, I can put an oxygen with 2 bonds, 2 lone pairs. Standard oxygen, 2 standard carbons, H with 1 bond. And that would be ethanol. A little bit friendlier alcohol than methanol. Methanol, don't drink that. It'll make you feel blind. Ethanol, don't drink that either. It'll make you get in trouble. Okay. Here you go. We put together a structure. It should be 20 valence electrons. We've already counted them, yeah? Can you do another structure? Put the oxygen in the middle. What about carbon, oxygen, carbon? H's on carbon. How many H's? We got 6. So 2 carbons now have 4 bonds, no lone pairs. And what do we want to put on the oxygen? 2 lone pairs for a total of 20 standard oxygen. For this formula, we came up with 2 different structures. What are they called? Isomers? What type of isomers are these? You're reading right there. Constitutional isomers. What's the definition of constitutional isomers? All isomers have the same formula. What does it mean, constitutional? Different arrangement of the atoms. Different connectivity. Over here, we have an oxygen only connected to 1 carbon. Over here, we have an oxygen connected to 2 carbons. Different connectivity. That's what constitutional isomers are. Same formula, different connectivity. Constitutional isomers have very different properties. This is probably a gas at room temperature. This is a liquid. Other different properties. When you get larger formulas, you can have maybe a huge number of constitutional isomers. This is an alcohol. Anybody know this one? Ether. Okay, we have to learn functional groups, the way we classify compounds. Name them. Question?
So how would you know the difference from it besides like actually having like the thing physically in front of you? Like
If I had 2 containers of these,
yeah, but like besides
I mean, they'd probably both be colorless liquids. This may be a gas at room temperature. But if it was cold, they'd both be colorless liquids. I mean, that gets into analysis, spectroscopy. IR spectroscopy. You easily tell the difference by IR. Okay? IR is going to be on the test point. One of them has an OH group. That can easily be seen in the IR. The other does not have an OH group. We use spectroscopy to see the molecules. different types of spectroscopy. Okay, let's try CH2O. Questions?
Carbon's formal charge energy 0.
We'll see carbon with a positive charge or a negative.
Okay.
We'll see positive more often. It's called a carbocation. See lots of those when we start reacting. The other would be a carbanion. Carbanion is also common, not quite as much. Okay, CH2O. This was now a spec of their CH4O. Okay, before CH4O, obviously we lost two H's here. We'll start talking about degrees of unsaturation. Your book calls it in chapter 15 or 16 hydrogen deficiency index. Kind of makes more sense. This is deficient by two H's compared to this. We're going to say that this has some unsaturation. We'll learn more about that as we go along. That's in the other handout. You can tell a lot from a formula. We can tell from this formula how many bonds are going to be in the structure. It's mentioned in the other handout. We're probably not going to cover that. All right? It's a little bit random. You don't need to do that. If you're interested. Let's do it and then see what else we can say about it. Valence electrons. Oh, we got 4,
12.
6, and 6, 12. Whatever we do, we need to have 12. Okay. I'm going to bond the carbon and oxygen together. I'm going to then try to fill the valence of carbon with H's. And so I'm going to put H and H. I only have 2 though, right? That carbon looks like it's begging for another H or something there. I got 2, 4, 6. Put 6 more up there. At this point, I recommend you then fill the valence of oxygen. Actually, the oxygen, we need to fill its valence first. Why? Because it's more electronegative. If we start filling the carbon first, that oxygen is going to get mad. All right? It wants the electrons more. Let's make it happy first. We're going to make it happy by putting how many lone pairs around it?
3.
3 lone pairs. Now the oxygen has an octet. How many electrons? 2, 4, 6, 8, 10, 12. Okay, they're all up there now. Don't put any more up there. Does every atom have an octet? Does carbon have an octet? No. 2, 4, 6. Oxygen does. Yes. Before we go on, though, that's actually a Lewis structure. It's not the best. That's charge. What's the charge of the carbon?
Positive.
How many does it own?
3.
It owns 3. It's supposed to have 4. It's missing 1. Positive. What's the charge of this?
Negative.
Negative. It's owning 7. 2, 4, 6, and 1 is 7, but it's only supposed to have 6. Okay? Note that this is neutral. See, that's neutral. If that was charged, I should have showed you a charge. I didn't show you a charge. It's net neutral. All right? But it's very important to have octets when you can. We'll talk more about that. This carbon needs another bond. We can do that by saying, hey, oxygen, I know you like electrons, but are you willing to share? Okay? Be a good friend. We're going to say, and what you want to do here, these electrons, I'm going to move them over here and make another bond. But the arrow movement is very important because we'll learn how to use arrows to show electron movement. And you will see me write WDAM. What does arrow mean? Okay? If you don't use your arrows correctly, I won't give you a WDAM. One student long ago said something like this, well, damn! Still remember. He was over there in the classroom. He said he got a well, damn on the quiz. Okay, what does this mean? I just moved electrons in and made another bond. All right, I'm going to use a double-headed arrow. This is going to be a resonance arrow, double-headed. What does that mean? It means this. I didn't move an H. I didn't move an H. I didn't do anything with the single bond. I didn't do anything with those two lone pairs. But the lone pair electrons are now what? They're now a bonding pair for an additional bond. We moved them in. They fell in and made an additional bond. It's really simplistic. Okay, we're not doing any higher level chemistry, PChem, or anything. Now we have this in between. Still the same number of electrons. Now does the carbon have an octet? How many around carbon? 2, 4, 6, 8. That's a double bond. But each bond is 2 electrons. And we can count 2, 4, 6, 8. Now we have an octet. How many around the oxygen? 2, 4, 6, 8. Now we have standard bonding for carbon. What's standard bonding? 4 bonds, no lone pairs? It's 4 bonds. Standard bonding for oxygen? 2 bonds, 2 lone pairs? 2 bonds? It just, the 2 bonds happens to be a double bond. Okay, any charge here? What's the charge of that carbon?
Neutral.
It's neutral. It owns 1 of each bond. 1, 2, 3, 4. Oxygen owns 1, 2, 3, 4, 5, 6. That's how many it's supposed to. Now everything's neutral. Which structure you like better?
The neutral one.
Typically, one without charge separation is better. Okay? This is what we're going to call the major resonance structure. Okay? No charges. Resonance is something we'll have to develop over the entire course, and I think in Chapter 3 we actually cover resonance. By the time we cover it, we will have alluded to it many times. Resonance is just an alternative way of showing the electrons, but you don't move any atoms. It's not constitutional isomers. Now, let's see over here. Let's just talk about a little bit. What about electronegativity? Do we have a dipole between carbon and oxygen?
Yes.
Which one's more electronegative?
Oxygen.
Oxygen. So we can show a dipole like that. That means even though we ask this oxygen to share, it's still sort of pooling. So these electrons are completely shared, but we're saying that oxygen hasn't been so greedy that it just stripped them away. The true structure is somewhere in between. The true structure, I'm changing the bond angles because we haven't got to that point yet. The true structure is probably like a partial bond. The second is kind of partial. The oxygen is sort of sharing, but not much. And the charges are somewhere in between. As the oxygen pulls these electrons towards it, it takes on more minus charge. Well, it doesn't pull it completely. Partial minus, and that's partial plus. See, this is the true structure, which takes into account the dipole. See, now we're getting to this kind of fuzziness. It's not discrete bonds. But that's real life. As chemists, we very often avoid these partial bonds, and we show these two and say the true structure is somewhere in between. Resonance structures are really fake structures. This is if you could see the compound, it would look more like this. Consequences of bond lengths. The bond length, is it like a single bond or a double? Well, it's actually somewhere in between. We'll say more about resonance as we go along. Important things here, how do we move this arrow? What does this arrow movement mean? Resonance arrow, this is not an equilibrium arrow. It's a double-headed resonance arrow. Major because no charge. So if someone asked to draw this, anybody know this compound? Formaldehyde. If anybody asks you to draw formaldehyde, I typically draw it like this. I mean, if you want to show off, you can draw it like that and talk to them about the dipole, but you know, you just have to know that type of stuff. So, because we needed to share, we didn't have enough valence electrons to do it without single bonds. We had to get, we only got the octet by sharing and making double bonds. Let's try one with HCN. How many valence electrons?
10.
10.
4, 5, and nitrogen has 5, 10. By the way, it's probably always going to be an even number. If it was an odd number, you'd have a lone electron, you'd have a radical. That's possible, but HCN, let's see, C to N. So now we got 2 electrons. Where do you want to put the H?
One carbon.
Stephen's recommended it carbon. Now we got 4 electrons up there.
Nitrogen has a lone pair.
No more atoms. Nitrogen's the greediest little guy here. Let's make him happy. Lone pairs. Do something like this. Now the nitrogen's full. 2, 4, 6, 8. Carbon, though, is not. What's the charge here? It's 2 plus. It's missing 2 electrons. Charge here?
2 negative.
2 negative. Okay? Now that is a Lewis structure, but it ain't the best. I mean, certainly we don't have an octet here. Octets are usually pretty major. Can we just start putting more electrons around the carbon? No, we don't have more electrons. What we're going to have to do here?
Triple bond.
We're going to have to say nitrogen, do you mind sharing here, okay? So let's take these electrons and move them in. What does that give? It's going to give us a structure with now a double bond between nitrogen and 2 lone pairs remaining.
There's still a charge.
What's the charge now?
Plus,
Plus
minus.
and minus. We still have 10 valence electrons. Well, that's better. We have less charge separation. Can we do something else?
Make a triple bond.
We can say, well, nitrogen, come on, do it one more time. These electrons, let's move them in here. What does that give? H, carbon, we now have 3 bonds here. How many lone pairs on the end now?
2.
Only 1 lone pair. Still 10 valence electrons. Now we don't have any charge. That's neutral, that's neutral. Standard bonding, carbon, 4 bonds, no lone pair. Standard bonding for nitrogen, 3 bonds, 1 lone pair. Now we have a good structure. That's HCN, hydrogen cyanide, very toxic gas. What do we end up having to have here? Triple bond. But you can tell that from the formula if you look at the handout I gave you. Again, that's a very miscellaneous thing. Most books probably don't even have that.
So if we were showing our work on this, do you want us to do the steps to show how we add each bond, or can we just show the triple bond?
Depending on what was asked.
Okay.
If you were asked to show Lewis structure, there you go.
Okay.
But this is like doing a math problem, you know, you probably need to, I would always recommend you do things very systematically. That's the way I will show you. All right? I did it very systematically. I connected certain things together. I filled the valence of carbon. I added electrons. I made pi bonds. Boom. Okay. Determining total number of bonds for formulas. It can be done. Look at the handout. Degrees of unsaturation or hydrogen index. HCN. Let's see if you can answer this. Probably not. How many H's can, if you add just CN, what's the maximum number of H's you can have? Well, look at this. CN, what if I put just H's all around it? And then put H's here, 1 lone pair.
5.
Can you put another H anywhere? You're not going to be able to put another H anywhere and not have standard bonding or create some charge. Okay? Formula there. C, H, 5, N. Okay? This is called saturated. Saturated in terms of hydrogens. One C and N together can take on a max of 5 H's. So when I see this, I see it's not saturated. It doesn't have 5 H's, it only has 1. So this is unsaturated, but by how much? Typically, every 2 H's are missing, that's 1 degree of unsaturation. So how many degrees of unsaturation is this? 2. 2 DUS. Well, it's missing 4 H's. Every 2 that you're missing is 1 degree. So you divide it by 2 essentially. If you're missing 4, that's 2 degrees of unsaturation. If you're missing 10 H's, that's 5 degrees of unsaturation. So this is 2 DUS compared to what saturated would be. Now, you can also look at structure. On the handout, I may go over this, I may go over the handout. But when you start making pi bonds, I haven't called it that yet, but when you start making the second bond and the third bond, you're making pi bonds. This has 2 pi bonds. Okay? We'll see this moving forward. Each pi bond is a DUS. That has 2 DUS. You see that from structure. I also see it from formula. Okay? Let's see where we're at. I think we need to, let me try to finish this up here. Okay, I did some here. There's others doing the workbook. Let's look at DUS a little bit more. Triple bonds, the charge. 5 bonds to carbon, not on this planet. Yeah, that's good. Another handout here. Okay, some of the handouts I'll give you what I call warm-ups. Okay, sort of got the term from Dr. Hager, but I don't do it like he does. Basically, be looking over what I call warm-ups and be prepared for discussion next time. Okay? For example, it says, how many DUS are in each drug above? How many DUS are in the following formulas? Well, we've already done HCN here. Functional groups. Hybridization. Okay? Front and back first page. This is type of stuff we're going to be moving on towards next time. I highly recommend you be prepared for class so you can get more out of it and you'll be ready to ask questions. Let's look at the DUS. Back here it says DUS. Basically it should be, well, it's all there. I want you to look at it, see if you understand it. We touched on it a little bit. And what I will do, instead of just covering it fresh, I'll just say any questions about this next time. Okay? DUS can be determined by structure or formula. Whenever you're putting together a structure, it's good to know how many DUS. If I know a compound has 5 degrees of unsaturation, I know that it's going to have, for example, 5 pi bonds. So it's very helpful in putting together a structure. Question?
On the, where it says like, is that an F or where it says like 1 second?
That's a T.
That's the,
It's a little bit odd. 1 double bond, 1 triple bond, that's a T. Please look at that. The other thing is functional groups. You're going to need to start learning your functional groups. Functional groups are just typical arrangements of atoms. So let's go to the second page. Instead of that, let me do this. I just took my cat to the vet, prescribed something here, and in the handout was in the drug packet. So I had to give my cat 3 of these pills. There's the compound. It's got about 20 carbons in it, yep? If you want the name, it's up there. Robenacoxib. It's a COX, like a COX-2 inhibitor for cats. Here's your fluorine. Functional groups. This is a common arrangement here. This is carboxylic acid. It's just a term we can call it. Now I can refer to it. Say, hey, look at the carboxylic acid. Carbon with 4 bonds. Oxygen. How many lone pairs on that oxygen?
2.
2. We know how many lone pairs. How many lone pairs here? 2. 2 bonds, 2 lone pairs. This is sort of an aniline or an amine. The rest is sort of aromatic. But your functional groups are just your typical arrangements of atoms. And then as we move on, we'll discuss the chemistry of different functional groups. Start learning those. We'll go through DUS and functional groups at the beginning of Thursday class. Before we dismiss, anything left open? Problems in the workbook, problems in the warm-up pages, and hopefully there's lots of questions on Thursday. Please check in the lab this week. Questions?
Why in HCN does H come before C? You said CH in alphabetical, but now it's HC.
Yeah, sometimes it's just common to call it HCN. A strict formula would be CHN, or CH.
Can you please send this forward? It's extra.
Yes,